joint work with myself and Andreas Holmesman and Alfredo Hubbard. So I'll start by explaining combinatorics of points in the plane. When you look at triples of points in the plane, here order is important, but they should be three distinct points. We define a function chi, which looks at the line going from one point to another point here from A to B, and it takes, for example, if you apply the function on ABC, it will be positive because this is a counterclockwise rotation, negative in the opposite, and zero if they're all on the line. And this is basically the sign of a determinant. And we call this function the order type of a family of points. So if you have several points, you look at among those points three at a time and see what sign those particular 3 points with that order have. And the order type then for a particular family of points will be a function which tells you for the 3 indices, just looking at integers 1 through n, what is the sign of the corresponding points in the plane? What is the orientation of the corresponding points in the plane? And in this case, we're only interested in generic families of points. So we'll only get plus and minus as a result, no zero, no 3 points on a single line. And we also have we can look at the inverse of this function, just the pre-image of a particular order type. This is the set of all families of n points in the plane, such that any triple of those points with a particular ordering have a prescribed sign under this function chi. So, and there's a well-known result saying something about the complexity. So if you look at any subset of the plane, or actually Rm, any Euclidean space defined by some strict polynomial inequalities. It's a theorem of Menev, the universality theorem. If you start with any such set, a strict basic semi-algebraic set, you can always find a family of points in the plane such that the realization space of this family of points in the plane modding out by isometries, because if you start with some points in the plane and you rotate these points around, you always preserve the order type, whether you take a line and you look at something on the left or right. That's independent of these rotations. So after you mod out by these rotations, you're left with any kind of subset of Rm that can be defined by polynomial inequalities. So the point of this is this shows you that these spaces can be very complicated, just knowing the combinatorics. So we would like to take these kinds of results, this result of Menev, and generalize it for families of convex subsets instead of points. So to do that, we have to say we would like this is kind of a topological result, so we need a topology on the space of the families of convex subsets. So the topology that we use is we have a metric defined by this Hausdorff metric. You can think of this as kind of a game where one player can pick a point on one set and the other player picks a point from the other set as close to the first point as they can, and then measure based on these if each player is choosing as best as they can. The first player wants to maximize the distance, the second player wants to minimize it. What will be the distance between those 2 points chosen? So in this example, the distance between the red set here and the blue set here, the first player would say choose a point in the red set here as far away from the blue set as possible, and the second player would choose something in the blue set as close to the first player's pick. And that distance, this will tell you the distance of between two subsets of the plane. And of course, if these two are the same set, then the distance will be 0, which is good. And we won't look at just any kind of family of subsets of the plane. We'll only look at ones that are convex and compact. And we also will have this non-crossing condition, which means that if we subtract one set from the other set, the result will be simply connected. So in this case, if you imagine, here's this blue set, if you remove this red set, you're still left with this simply connected region. But if I took the end of this red set and cooled it across this blue set, to break it into two pieces, that would be not allowed. So, and then there's an equivalent characterization of these kinds of convex, compact subsets of the plane, which is that they should have two tangents. Always two double tangents between these two sets. And we always, when we look at the tangent line, we always pick a particular orientation of this double tangent so that both bodies are on the left side of the oriented tangent line, common tangent line. So, now similar to points in the plane, we'll define an order type for these convex bodies in the plane. And this will be similar, but with some differences. Here, again, we look at, instead of a line going through 2 points, we have a line that's tangent to a pair of points. And we orient it so that we look at this line, we choose an orientation, the line from A to B. This is what allows us to distinguish between left and right. We always choose it so that both bodies are on the left again. And then we say that a triple, here ABC is positive, if C is on the left of the tangent, the double tangent that A and B are both on the left of. And it could be the case that C is also tangent. I mean, we will not consider that case here, but if a set crosses that line, then we say the orientation of those three is negative with that ordering. So this is similar to looking at clockwise and counterclockwise. And you can also define this using determinants in a similar way, but I didn't write that. So, I mean, you start with a...
When is it clear?
Pardon?
When is it clear?
So, it would be 0. So if C is completely within this half space, then it's plus. If you move the set so that it just touches this line, that would be 0. Then you have a single line which is simultaneously tangent to three convex bodies on the left. And then if it crosses, it's negative.
So if any amount of D is on the other side
Yes.
of the open half plane, then it's negative.
That's right, yes. Any amount of D, well, on the other side of the closed half plane, actually, because if it just touches the boundary.
So if it's just a point on, or if it's just a line segment that's just this.
Yeah, so if it were a point just here, that would be 0.
Okay.
But actually, we'll see we're not going to worry about those cases, so. And then the same way, we have a whole bunch of these convex, compact subsets of the plane, and we'll define an order type in the same way. We'll pick an order triple, and then look at this line and see if it's on the left or if it crosses. And again, we always assume that we never get 0. Many of these things generalize to cases where they get 0, but for us, we'll ignore that case. So, and similarly, the realization space is defined. We can look at triples of indices and assign to that positive or negative, and then look at now all families of convex bodies in the plane so that if you pick out the triple with those indices, with that order, you get the same sign. And now we have this new result. This may be surprising, possibly given the title of the talk, but we'll see a twist at the end. In this case, if you're just looking at convex bodies in the plane, all of the topology goes away except the isometries of the plane. If you, of course, if you have a bunch of convex bodies and you rotate them, this being on the left property will be preserved by those rotations. So, but if you mine out by those rotations and you look at a family of convex bodies with a prescribed order type, that space will always be contractible. So this is even a non-crossing, which allows us to define the order type. So here's a way that you can see that. So what we'll do is we'll start with a particular family and we'll look at tangent lines and we'll construct a canonical example. So the way we do this first is we pick a particular direction and we will look at the tangents just in that direction in their order. And we'll start constructing our new set will be in these circles going around. So the first thing we do is we see, as we continue in this direction, we'll continue around this circle, and every time we get to a tangent line here, we'll draw these corresponding lines crossing. So here we have a tangent line going from, I guess, yellow to purple. So here yellow curves upward and purple curves downward. And then we look at the next tangent and we do the same corresponding crossing, and then another one. Now, if we take these circles and we squeeze them close enough together, then we can ensure, the way I draw it here, they don't quite look convex. But we could take these circles and make them very close together. And if we do that, then we can make all of these, the resulting bodies that we get as we travel around these concentric circles to be convex. So here, continuing this process around, we'll get some yellow body and some purple body. And the important thing to note here is that every tangent, double tangent, between the original bodies and the new bodies that we're constructing will be the same. Parallel, sorry. The same direction. And that's important because if you take a Minkowski average of two convex bodies, of pairs of convex bodies, you'll always preserve the direction of these tangents. If the directions of the tangents are the same, then when you take a Minkowski sum of the pair of bodies that have the same tangent between them, you'll still have that same tangent between them. So the result of that is we can basically linear interpolation by doing Minkowski sums and go straight from this convex bodies to the result that we get by traveling around these circles and including the crossings to always having these bodies, the boundaries cross each other so that we always get the same tangent that we started with. So in this way, what we get is we get a function from the torus of 2n choose 2 directions to convex bodies in the plane, to collections of n convex bodies in the plane, so that the double tangents between those convex bodies in the plane are whatever vectors you picked in this torus. So this torus has two vectors for two tangent directions for every pair of convex bodies, right? And the process that I described will construct a collection of convex bodies, a particular collection of convex bodies in the plane, so that whatever those pairs are that you picked out, those will be the double tangents of the resulting convex bodies. So, if you look at the realization space of some order type, then you can say, let's fix all the tangent directions and find the corresponding canonical convex body with these tangent directions. And then you take a Minkowski sum to go directly to those convex bodies. So this gives you a fibration over some subset of the torus of dimension 2n choose 2, where the resulting bodies with those tangents has the order type that you started with. And then from there you have to see that if you have certain ordering constraints. So here the result of what this space looks like is basically with points around the circle that have to be ordered in a certain way. They don't all have to be ordered, but enough of them have to be ordered so that the only overall the only topology that you get in this space is turning the circle completely around, turning all of the points completely around. I mean, if they were all linearly ordered around the circle, this would obviously be the case. The only thing you could do, besides moving things a little bit, is to spin the entire circle around. But in this case, there's a little bit more. So the topic of the talk is to show a universality theorem. So we'll get to that. Instead of looking at general convex bodies, if we just look at k-gons in the plane. So here we'll start with an order type and we'll just look at collections of k-gons. Every convex body should have k vertices. So that when we look at any triple, we have a particular sign. So we start with here, this script f specifies a sign on triples of indices. We have a result now that says this satisfies a universality theorem. So this is, you can start with, if you recall from before the definition of a strict basic semi-algebraic set, this is a set in Rm which is defined by the intersection of a system of strict polynomial inequalities. And if you start with any strict polynomial inequalities, there's some corresponding function on from triples of indices to plus and minus, so that the space of k-gons with this particular order type, with the order type given by this function from triples of indices to plus or minus, will be, up to isometries of the plane, will be homotopic to this strict basic semi-algebraic set. So we can see a little bit about why that's true. So the first thing to note is that if you pick out two bodies, say here BI is the red one and BJ is the green one, and every other one, the rest of them say are these blue ones, you always get a positive sign. That means they're always on the left of this double tangent. Then that means that this tangent line would be a supporting edge of the convex hull of all of these bodies. So the result is that if you look at some of the information that you can get from the order type, is you can read off which bodies are on the convex hull of the entire thing. If you take the convex hull of this collection of bodies by looking at this condition, you can go around the outside and read off one by one. And let's say in the case, in our case, we'll choose k to be equal to 4. Making that choice, if we require that one of the bodies meet the boundary at 4 times, which we can do from the order type by having, saying that, for example, here, these two, and then anything else, these, the red one, the green one, and anything else will be positive. And we have a similar relation for every pair along the boundary. Then, this imposes a great deal of restriction on where the vertices of the red k-gon can be, the red quadrilateral can be, because it has to have, if you look between these two blue ones, there has to be one vertex that meets the convex hull between them. If you look between the blue one and the green one, there has to be a piece that sticks out. And if we have 4 places, then you know where those 4 vertices, where those 4 vertices are. If we say instead that k was 3, then this arrangement would be impossible, because we would have to have 4 separate points that meet on the boundary of the convex hull, which we couldn't do. So, using this property, we can find particular points in the plane that have a specified order type, which we get from the order type of the convex sets. So, in this case here, as we go around the boundary of this circle, we start with all 3 of the red quadrilaterals have to meet in one section of this, the convex hull here. And then, if you look just look at the blue ones and one of the red ones at a time. Right? Just the blue ones and and say this first one, red one at a time, tells you that you have to have a red vertex between these 2 blue quadrilaterals, these 2 blue polygons, and then you have to have a red vertex between these 2 blue polygons, and so on all the way around. So that between these 2 blue polygons, each of the red polygons has one vertex in the region, exactly one vertex. And the rest of the order type between the red polygons is always in convex position. The only place where you have some freedom left is in how these vertices at the bottom are arranged. And here, if you look at so here I've drawn the triangle so that the middle guy is further in towards the center here. And this is because this right one, these 2 red ones, and the last red one here are in a negative orientation. And I could switch it so that they're in a positive orientation, and then he would have to be, the red vertex in the middle would have to be below this line. This is, but the result is that I can control the orientation of all the single vertices here. So, because of that, if I want to get any order type for points, what I can do is I can start with some order type for points that I want to get, and I can determine the order type for convex sets such that there will be particular points among those convex sets which have this specified order type. And the rest of the convex sets will be more of a trivial realization space. So this is a picture of how you do that. If you start with some points in the plane, pick out, you can always find somewhere, pick out one of the vertices that's on the convex hull of all of them, and then you can see, as you sweep through the point set, based on the order type, which vertex you hit. So you can see that first you hit this vertex, and if you come from here, then this one comes next, and this one comes next as you go in a particular direction. And you can find another point in the plane close to that point, so that you see everything in the same direction except the point that you started at that you just left. So if I say start at this point and then move out to the top there, then as I sweep from the point at the top, I'll see each of the points in the black points which I started with in the point set in the same order. And then from this we have to construct convex sets. So the way we can do that is cross all of these lines from the new point to the points of the point set that I started with, the family of points that I started with an ellipse. So if I have an ellipse and I put a bunch of points along the ellipse, these points will be in convex position. So this means that I can construct a polygon, a collection of polygons, by, for every point here, for every point on the point set, I have a polygon that comes very close to the line leading up to the single point until it reaches this ellipse. And then on the ellipse there will be an interval in which I alternate, this polygon alternates between the large polygon, which has one of its vertices at this point, and points along the outside of the ellipse. And so the result is that in this picture it's kind of hard to see because these things become very small and spread out. But this is basically the same picture as here, just it's shrunk along the ellipse, where these smaller blue polygons force the remaining vertices of these red polygons to be in a particular configuration. So I think that's all actually. I think I went through much faster. Is there some questions about
when the punchline appear, can you sketch the punchline of this?
Okay, so the result. No, so I want to go in two directions. I want to go from so I want to say if you start with any family of points in the plane, then you can find a family of convex sets, so that these convex sets can only be realized if you can realize this family of points in the plane. And furthermore, all the realizations of the convex sets will form the space can be decomposed into fibers. So I'll go back to the original Minev result. So the way the proof works is it uses this result of Minev by saying, okay, you start with a list of strict polynomial inequalities, right? And Minev says from this list of strict polynomial inequalities, you can get a bunch of points in the plane so that the resulting realization space will be homotopic to the space that you specified by these polynomials. So an example is like, I could say x squared plus y squared is between 1 and 2, right? So then I get a space that looks like this annulus here, right? And then I pick out some point in this annulus, and for each point in the annulus, there's some arrangement of points in the plane. I don't know what they look like, but these cannot just be scattered anywhere. They're arranged in a very special way, so that every point in this annulus corresponds to a point set with that same order type, and anything with that order type projects to some point in this annulus, right? So to get the same result for families of convex sets rather than families of points, now I still have this pair of equations, and you could put in a bunch of equations. You could make it disconnected. You could make it have higher topologies. Maybe if you want, you could make a sphere. Oops. Whatever kind of polynomial inequalities you want. So from this point set then, there's a corresponding order type for convex bodies, so that just k-gons. So that any realization of these k-gons projects to some points in the planes, projects to a family of points in the plane, which then projects to a point in the strict basic semi-algebraic set. So the way to go from points, these points, to, in this case, quadrilaterals, is here you just have 3 points. And you know what the order type for these 3 points is going to be. This, the realization space at the top here will be any convex curve you like. And at the bottom, in the case of just 3 points, you don't have anything interesting. But you could have many, many more than 3 points. As many points as you like. You can always make a construction like this, following this technique. So, is it all right? Are there other questions? Did you?
So now how many bodies do you get?
So
this point set.
So you will get well, so it depends both on the point set and on K. You will get
K times n.
Kn plus 1. So if you have n points in the plane, then it will take Kn plus 1 points. So here, if I had a mouse, here you have one of these small blue polygons, and then for every point in the plane, you have a line here, and then a red polygon, and K minus 1 blue polygon separating the vertices, the remaining vertices. So you could choose K to be 0. And if K is 0, then this construction is completely trivial. It's exactly the nav. Your 0 gons are just points in the plane, just the points in the plane that you started with. Or if you choose K to be 2, then your 2 gons would be line segments. Right? Then this would be literally just a line from this point up to the ellipse.
So they're 1 gons points.
What? Yes. Oh, sorry. One gons. Yes. Sorry. Yeah. Okay.
Any other questions?
Yeah, so
So one of the theorems says that this realization space modular isometry is contractible and for convex bodies. And then the other theorem says for K-gons it's not contractible. But so are there any contradictions?
Right. So this is a subtle point, right? So we have two realization spaces. One space. So both of these spaces are collections of K-gons with this Hausdorff metric.
Not K-gons, right?
Oh, sorry, yeah, but they're both convex bodies with this Hausdorff metric. Here, yes. So this gives you the topology, but you're restricted in what the space can look like. In the one case, your realizations should be any kind of convex body, which means they can be curved. So what happens due to these? This is a good point, right? I could try to do the same construction with I have this point set. I project everything, say, to here. Okay, and then I find these K-gons. This is how the process goes, right? Now, if you look at points in the plane, each point, all these lines passing through it gives you a pencil of lines, right? That all pass through a single point, and that pencil of lines allows you to do projections from one line to another. So if I have one line here, and then I may have another line here, and then I have if I have a point in my point set, this pencil of lines passing through this single point allows me to take these points on this top line here and project it down to some other line. This is the kind of thing that you can do. And being able to do these projections is part of where the universality comes from. Now, if I have a bunch of points, if I have a K-gon that comes to a single point, right, and I can have a pencil of lines going through that are all tangent to the single point. If I then, instead of having a single point, I loosen the condition of having K-gons to just general convex bodies, what that allows me to do is to then have these tangents all separate from each other. So now all of these tangent lines are not going through the same point. These tangent lines are maybe going through some different points. And I lose this projection. So that's really where, that's the key to having these K-gons rather than general convex bodies. But this brings up a bunch of other questions, because here at one point you have all of universality, and then at the other point you have nothing, basically. Just a completely trivial topological space. There should be something in between where either maybe there's a certain critical point where you suddenly go from having no topology to everything, or you may go through a growth of complexity, where as you require more or less vertices, in some, say the number of vertices going to n, going as some function of n, like n squared vertices or something, you may get some degree of your polynomials. So this is some possible questions that we can look at in the future. So this was the other realization space. These ones all have to be polygons. So,
and to follow up on something like that, if something like this were to exist, maybe do you have something like, by specifying, upper bounds on the Betty numbers, and we can realize this kind of order type, something like this? I mean,
maybe. So
how do you want to separate the sequence of going from contractible to getting everything. Do you have a proposal?
So one thing that you can look at is the way we define these spaces. I mean, so we don't have that clear of an idea yet. I mean, we have some idea, but the way we define these spaces, a triangle is just a degenerate kind of quadrilateral, right? So as you add in more and more vertices, what you get is you get some space that's going. So maybe your realization space looks something like this, one of them looks something like this, and then the next one, if you add in a vertex, maybe you lose this hole, right? But maybe the other one you keep. Okay, so maybe the area inside the white could represent, say, triangles, and then maybe the area that's red could represent, say, quadrilaterals. Right, this covers up maybe one hole, but not another. I mean,
With the same order type.
with the same order type as you add vertices. The other thing that we're looking at now is we think that it is the case that, and we have some evidence of this, that if you allow n squared, k to be equal to n squared, then you do get the trivial topology. You get a contractible space. But this is something we're still in the process of working out all the details of. So, are there other questions?
Okay, so now let's thank the speaker.